Okay, so as always, let's start with a small review of our last lecture. So last time we were talking about the effect of altitude on thrust and power values, right? Both required and available values. And I'm just quickly scrolling through this. So basically for thrust required, the thrust required curves shift to the right as air density values get lower. The minimum value doesn't change. Okay, the minimum thrust required value is always the same. It's just that at different altitudes, that minimum thrust is achieved at different speeds. Okay, and if you take a look at power, the situation is as follows. The power required curves shift to the right and up at the same time, which is expected, right? Because if you remember, if you draw a straight line from the origin tangent to the power required curve, then the point where these two are tangents happens to be the same point where the thrust required is minimum. Okay, and since and also the slope here, the tangent of the angle here gives you the minimum thrust required value. And since the minimum thrust required value doesn't change, that means the slope doesn't change. So from here you can also conclude that at different altitudes the power required curve slides along this line here. The available thrust and power depend on altitude as well, and the dependence there is linear. So we use these relations to represent that. So if the air density is half, for example, then the available thrust or available power will be half as well. Okay, so from the two, you can easily see that if, for example, at a certain altitude you have thrust required or power required can be used as well, and thrust available are like this. As the aircraft climbs to higher altitudes, the thrust required will be shifting to the right, and the available thrust will be coming down. Okay, so the gap here, the gap between the two will be getting smaller and smaller. And finally, when you come to there's an altitude at which point the two will become coinciding at one point only. Okay, and if you keep climbing, then there will be no intersection at all. The thrust required will be higher than the available thrust at all speeds. So at this point, the altitude corresponding to this point is called the absolute ceiling. And the important thing here is the absolute ceiling can be achieved at one speed only. Okay, so you have to be flying at this particular speed, otherwise you can't really have a steady level flight at that altitude at any other speed. Okay, so let's start today's lecture with an example. So I'll be using this example. So we have an aircraft. This is a propeller aircraft. We can tell this from this information. The maximum engine power is given. Remember, for propeller aircraft, you talk about engine power because it's a constant number with respect to speed. If this was a jet aircraft, then engine thrust would be provided. So, and as we just said, available power and thrust depend on altitude. So whenever you see a number, numbers are almost always given for sea level. Okay, so most of the time you don't see that explicitly stated that value is valid for sea level, but you can assume that it is valid for sea level only. So this aircraft is given to have a 230 horsepower engine at sea level, and horsepower is the unit of power, and just like watt. So since in our equations we use the metric system, we need to use power in terms of watts, and you can convert horsepower to watt by using this scaling factor. So 1 horsepower is approximately 746 watts. So that means the engine power is this much in terms of watts. The Prandtl drag coefficient is given, and then the other this K coefficient for the induced drag can be calculated using these numbers. The Oswald efficiency factor and the other aspect ratio can be found from here. Okay, there's also this efficiency number. This is the propeller efficiency. It is just a number that you use to reduce the engine power. So the engine produces this much power at maximum throttle, but not all that power is transmitted to flight. That's because while the propeller is rotating, some power needs to be spent to overcome propeller drag force. So anyway, to account for that power lost to that, an efficiency factor is used. So you basically multiply the engine power with this factor. This is an approximation, obviously. This is not a constant number. And at different speeds, propellers have different efficiencies. But it is good enough to use a fixed number for propeller efficiency. Okay, so the question asks us to calculate the thrust and power required values at sea level and at this particular speed. Okay, so at 61 meters per second. So the calculations are really simple. First, you find what should the lift coefficient be for that speed and for that altitude. It turns out that the lift coefficient has to be this much, and from there we can find the drag coefficient, and the required thrust force turns out to be this much. If you find the power at that 61 meter per second speed and convert that to horsepower, it turns out that the aircraft needs 96 horsepower. And if you take propeller efficiency into account, for this much power to be transmitted to flight, the engine should actually be producing this much power. Okay, 120 horsepower at sea level. And this corresponds to 52% of the total engine power, the maximum engine power. So we say that we conclude that the engine should be operating at 52% of its maximum power for this flight to take place. So let me just remove this part first. So this is the thrust required curve, and at 61 meters per second, the required thrust force is this much in newtons, and this corresponds to 52% of the total engine power. Okay, and for this aircraft, we can also calculate the minimum thrust required value and the minimum the speed for a minimum thrust required, or you can also calculate the maximum speed for this altitude. So if the pilot gives full power, in that case the engine will be producing more power, and for the steady level flight speed it can be calculated for that case as well. So anyway, the calculations are all here. We can take a look at this later on. So it turns out that the maximum speed is about 80 meters per second for this aircraft at the given altitude. Okay, so maybe I should mention this here. There's already a note here. To calculate the power, you have this equation in terms of speed, right? And you need to solve for speed out of that equation. In this case, you have a fourth order polynomial in V, and that has 4 solutions. So these 2 solutions are obviously irrelevant. They are complex numbers. There are 2 real solutions. This is the one we're looking for, and the other solution, this small number, corresponds to the other intersection point, right? We don't see it here, but if you extend these curves, this goes up like that, and then you extend this one here, and the other intersection point corresponds to this one, this small number, about 6 point something meters per second. So obviously in this case it is not a valid flight speed, right? No real aircraft can fly that slowly. If you have a small UAV, then this may be a valid flight speed, but for a real aircraft, this is not a valid flight speed because the aircraft will stall before that. So in this case, the stalling speed will be the minimum speed. So what I'm saying is the power required curve will be doing like this, and this point corresponds to the stall point. In this case, the limiting factor for minimum speed becomes the stall speed. But at a different altitude, the limiting factor may become the engine power. So there are two possibilities for that. Okay. Let's see if there's anything else I would like to say here. Okay, I think we can start talking about now the climbing flight. So if you remember, before we started this steady level flight condition, we started with a more general case, right? We drew the diagram for the most general flight, and then we put the forces on this diagram, and then we wrote the most general equations for longitudinal flight, and then we did a lot of simplifications. If you remember that, we said it's a steady flight, then we equated all the acceleration terms to 0, and then we said it's a level flight, and that meant the flight path angle is 0, and then after all those simplifications we arrived at these simple equations, right? Lift should be equal to the weight and thrust should be equal to the drag force. And that's what we were talking about so far. Now we're relaxing one of the assumptions to make it a more general case. And this time we're saying that let the aircraft be climbing instead of doing a level flight. Let's consider the case where the flight path angle is not 0. Okay, so everything else is still valid, all the other assumptions, including the steady flight. The acceleration terms are still 0. Still the speed of the flight does not change, but the flight path angle is this time non-zero. So in this case, the velocity vector for the aircraft is this one. It makes an angle with horizontal. We call that flight path angle gamma. And in this case, the speed has two components, right? There's a horizontal component and the vertical component, and these two components are obtained through these trigonometric relations. So by definition, rate of climb is how fast an aircraft climbs. So in other words, the rate of climb is defined as the vertical speed of an aircraft. Okay, so this W is the speed in the vertical axis, and that is equal to the rate of climb of an aircraft. Okay, so here it says the only difference between a steady level flight and a steady climb is that in the former, flight path angle gamma is 0, whereas in the climbing case, gamma is a positive angle. Everything else is the same. And W, which is the vertical component of the speed, is called the rate of climb. Okay, now let's take a look at the equations for this case. If you write the forces, again we write the force equality in two axes. First we write them in the axis which is parallel to the flight path, and then we write the forces in the axis perpendicular to that. And then the two equations for those two axes are these two equations here. So in this axis you have the thrust force and the drag force, but in addition the weight of the aircraft has some component along that axis, so that brings you this term. And in the other axis you have the lift force, and thrust and drag have no component in that axis, but weight has obviously a component there, and that's given by V times cosine gamma. So obviously if you set gamma equal to 0, you go back to the previous equations, yeah? Right? For gamma is equal to 0, these two equations are valid, but for the climbing case, these terms are introduced into the equation. One interesting thing here is, for steady level flight, lift should be equal to the weight of the aircraft, right? But for climbing flight, that's not necessary. The lift can actually be less than the weight of the aircraft because it only carries a part of the weight and not the entire weight of the aircraft, right? And the remaining part is carried by the thrust force. Okay? So we take this equation and we do the following. We divide this entire equation with the weight of the aircraft and multiply it with the speed. Okay, so it doesn't change anything. We do this to both sides of the equation. And this is what we get. We throw this d to the other side. So we have t minus d. Multiply that by v and divide it by weight. So this is what we have on the left. On the right hand side, this w gets cancelled and it's multiplied by v, the speed of the flight. Okay. So if you look at the right hand side now of this equation, what we have on the right hand side is nothing but the speed, the rate of climb, right? So this is the vertical component of the speed of flight. So now we have obtained an equation for the rate of climb. Okay, so it looks like, well, it turns out that the rate of climb is given by the difference between the thrust force and the drag force multiplied by v infinity divided by weight. Okay, so let's take a look at this expression. So on the left hand side we have t times v minus d times v. So whenever you have a force multiplied by speed, that gives you power, right? Remember this from our previous lectures. So on one side you have thrust times speed. So this is actually the power, right? The power transferred to flight by the engine. And on the right hand side you have drag force times the speed. And this is in fact the power consumed by flight. So these are both power terms. This is the engine thrust times the speed, the engine power. This is drag times speed. This is the power consumed by flight. And since this is the difference between two power terms, it is called excess power, right? And so for the steady level flight, we said power required should be equal to the power available. Then that was because thrust was equal to the drag. But this time we don't have that equality anymore. So for again steady level flight, thrust was assumed to be equal to drag force, and we also called this required thrust. And the engine thrust was supposed to be equal to that. So all of these things were the same thing. But this time they're not equal anymore. Okay. So this is the available thrust, available power, and this is the required power. Okay. So the available power minus the required power is called the excess power, and if you divide that by the v, the entire thing gives you the rate of climb of your aircraft. Okay, so here it says what I just explained is written here. In a steady level flight, thrust of the engine should be equal to the drag force, and this is also called the required thrust. And in that case, the excess power is equal to 0. So the entire power is consumed by flight. But in the case where the two are not equal, when you have more thrust force than the drag force, then there's a certain difference, and that difference multiplied by the speed is called the excess power. So while in steady level flight, engine thrust should be equal to drag. To maintain a steady climb, the aircraft needs to have positive excess power, which means the engine thrust should be greater than the drag force. Okay? And the reason is apparent here. The engine needs to provide more force than drag force because some of that force goes to supporting the weight, a part of the weight of the aircraft. Okay. So since the rate of climb depends on excess power, for climbing flight, it is easier to use the power curves instead of the thrust curve. Okay, so if you want to study the climbing performance of an aircraft, then it is easier to use the power curve. Okay, now let's remember the previous example. Remember, we had a propeller aircraft, and that aircraft was, this was the power required. The engine power was set to 52%. I think it was 52, right? 52. 52% of TA max, and the intersection was at 61 meters per second. Okay, so the PA is equal to PR. There's no difference here, and the excess power is equal to 0. So to start climbing, you need to provide more power into flight than what is consumed by the drag force. So suppose that the pilot increases engine power to 100%, then the power available curve will go up. That's 100% of PA max. Now you're still flying at this speed, at 61 meters per second. When the pilot does that and the aircraft is still flying at this speed, now the difference between the two is the excess power. Okay, so this is, let me use it, show it with red color. So this is PA minus PR, and that is equal to the excess power. Okay, so suppose that again we go back to that example, and the aircraft was initially flying at 61 meters per second by at 52% engine power. The pilot increases the power to 100%, and he gets well, I guess we need to go down to find the actual excess power. Okay, so the excess power the aircraft gets in that case is this much. Okay, so this is the full engine power that can be transmitted to flight, and this is obtained by the full power times the propeller efficiency. So this much power can be transmitted to flight at full throttle, and at 52% the power was this much. So as soon as the pilot gives full power, then this much excess power is obtained, and if this power turns into climb, the rate of climb is obtained by dividing the excess power to the weight of the aircraft, right? Okay, so that's coming from this relation here. So the original thrust was equal to drag force, or available power was equal to the required power, and the excess power was 0. But as soon as the pilot increased the available power, then a certain excess power is generated, and that excess power divided by the weight of the aircraft gives you the rate of climb. Okay? Okay, so for that aircraft, the rate of climb the aircraft can achieve is 5 meters per second at full power and at that altitude. And at that speed, by the way, so this depends on speed as well. Okay, is this clear? Do you have any questions? Well, here the next two slides explain or remind you that this is valid for steady conditions. So if you are flying, as soon as you increase engine power, you don't go from one steady flight case to another steady flight case, right? Things start changing. So as soon as you increase power, the aircraft now, since it has more power, it will tend to accelerate, right? There is more thrust force, so that should cause a variation in a change in its speed. So the pilot here can choose what to do with that additional thrust force, right? So if the pilot wants to accelerate, then the power will accelerate the aircraft instead of causing a climbing flight. But the pilot can choose that by adjusting the elevator angle appropriately. So we're assuming that, okay, so at this point, so now the horizontal axis is time, okay? So initially, the aircraft was doing a steady flight, so the speed was constant, it was not changing with respect to time. Or similarly, the altitude was constant as well at sea level. As the power is increased, these things will be changing, okay? So the speed will be changing. And how it changes depends on how the pilot controls the elevator. As a result, the altitude will be changing as well. So we're assuming that the pilot brings the aircraft to another steady condition. So he keeps the elevator fixed at a certain angle such that the speed of the flight is back to 61 meters per second after these variations. And the altitude is increasing steadily at a constant rate of 5 meters per second. Okay? So otherwise the pilot can choose this additional power differently. So he can choose to increase the speed of the aircraft, but we will see that later. So right now we're assuming that the additional power is used for climbing. Okay? And also here, even though I say this is a steady climb, it's not exactly steady, because when this climb starts, it has a rate of climb of 5 meters per second. But if it climbs, let's say for 5 minutes, after 5 minutes, it is 300 seconds, right? After 300 seconds, the aircraft altitude will be increased by 1.5 kilometers. And so this was 61 meters per second. So this is the conditions at sea level. But after 1.5 kilometers, things will be different, right? The required power will be shifted like that. And then the available power will be shifted as well. Let me show that like this. So the red curves are for this is h is equal to 1.5 kilometers. Excess power at 1.5 kilometers is less than excess power at sea level. At sea level. And hence the rate of climb will be smaller, right? Smaller than 5 meters per second. Let me just switch to typing. But the reduction in power is really slow, so we can still call it a steady climb. So I guess that was already shown here. Okay, now let me ask you a question and let's think about that case. Let me now copy all of this. So we said that for the sample aircraft, when it was originally flying at 61 meters per second, by increasing the engine power, the pilot gets additional power, and that additional power is can be used for climbing. Now let me just remove these red ones. Okay, now let's say so this is PA max, right? And remember this was 52% of PA max. Okay, now let's assume that the aircraft was initially flying at its maximum speed, which was 79.7 meters per second, if I remember correctly. This was 79.7. And this was already at maximum power, okay? Suppose that instead of flying at 61 meters per second, the aircraft was initially flying at 79.7 meters per second at full power. It was doing a steady level flight. So, do you think the aircraft can climb in that condition? Remember, for a steady climb, you need excess power, right? But at this speed, the power required is already equal to the maximum engine power, right? So you cannot really have excess power at this speed. So that means if an aircraft flies at its maximum velocity at a given altitude, that aircraft cannot perform a climb. Because to be able to climb, you need to have more power than what is required by the flight. And since your engine is already running at its full power, you cannot increase this, right? You cannot do that and get excess power because you don't have more power you can get out of your engine. So again, an aircraft flying at its maximum speed cannot perform a steady climb at all. Okay? So if this aircraft was flying at its maximum speed, and if the pilot needs to climb, then what he needs to do is he needs to get excess power, right? You need to have excess power, which is equal to PA minus PR, greater than 0. And if your PA is already set to maximum, the only way to get excess power is to make this smaller, okay? So if the aircraft was originally flying at its maximum speed, to be able to climb, the pilot needs to slow down first. Okay, the pilot needs to come to a lower speed where the required power is smaller than the maximum available power, and only after that the aircraft can start climbing. Okay? Hı? Doğru tabii. Hı hı. So that's a very good point. So what I just said is valid only for steady climb. Otherwise, if you have an aircraft flying at maximum speed, and if the pilot increases the elevator angle to pitch up, then the equilibrium will be disturbed. Okay, so up from that point on, it's not going to be an equilibrium flight anymore. But if the pilot increases the pitch angle, which will increase the angle of attack, and that will change things, and it is up to the pilot what to do. He can come to a new steady condition, and this new steady condition can be a steady level flight or a steady climb or a steady descent, and only after that we can go back to these plots and these equations. Okay, so all of these plots are always only valid for a steady case. So that's what I tried to explain up here. Neredeydi? Geçtik mi? Okay, so this is what I was saying here. When things are stationary, when things are steady, we use these equations. But during the times when things are changing, we can't use these plots anymore. So obviously, if you are flying at maximum speed, the pilot can try to climb, right, by by pitching up the aircraft, basically. But as soon as he does that, things will start changing, because if he starts a climbing flight, then the speed of the aircraft will be going down, right? So effectively, it will be doing doing what I just said earlier. So as soon as he tries to climb, the speed of the aircraft will be going down, and that will reduce the required power. And then, since the engine is still running at full power, there will be some excess power produced, and that excess power will allow the aircraft to climb. Okay, so let me just say this and then we can take a break. So if you compare propeller and jet aircraft, then you will see that there's an important difference in their climb abilities. So the blue curves are the required power curves for an aircraft. And if this aircraft if it's propelled by a propeller, then the available power will be constant at all speeds, right? So this is the available power. But if the aircraft is propelled by a jet engine, then since the thrust is constant, the available power will be this line. Okay? So if you look at these two, then you can see that the propeller aircraft has better climbing performance at low speed, because at low speed you can get a very large excess power from a propeller. Whereas if you have a jet aircraft at low speed, since the available power is low as well, the excess power is smaller. Okay, so this is an important difference between a propeller and a jet aircraft. Okay, do you have any questions? So let's give a break and then continue after the break.